Last week we looked at, this unit, combinations of functions, is when we have some kind of, like, probably real life situation. I mean, that's the point of mathematics, right? Modeling problems in the real world. So we have some kind of real life situation that can't be modeled with one single function, right? It's not linear, it's not quadratic, it's not one of these functions. So far, if you think about all of high school, you do a lot of modeling real world circumstances with mathematics, but like it's a ball being thrown in the air, so it's just quadratic, right? You don't even think about air resistance or anything like that. So now we're combining functions in the same question to more accurately model whatever it is you're trying to do. Now, we won't get that far with this, but we'll see today a glimpse of how this is useful. And then last week we talked about adding and subtracting functions, and really the big idea there to me was if I have f at x and I have g at x, f plus g only exists where both on the domain where both f and g exist, right? So, and we saw an example of that the domain of a combination of two functions is the overlap of the domains of those two functions. So it only exists, f plus g only exists where both f and g exist, where you can actually add the y values together. Some people might think, oh, you just consider it 0 everywhere else. No. And that's the same with products and quotients, where the domain of the product or quotient of two functions the domain is the overlap of the two original functions that you're taking the product or quotient of. So here's a simple example, very straightforward. You'll notice the work in the textbook is pretty simple as well, where we have two graphs, but again, like I said, it's great review. So f at x is x plus 3. It's this green one, f at x. And g at x is this red one. It's a quadratic. It opens downwards. And it's graphed here for us. But you could kind of see that you could factor it, or complete the square would be a bit of a decimal, but you could do that to figure out what the graph is. And this guy here is g at x. And so all we're going to do is we're going to find the value of each of the... Now, so here's the thing that's nice review. These are both polynomial functions. What do we know about polynomial functions? Part of the definition, or one of the standard properties of a polynomial function, is that their domain is x is an element of the real numbers. Every polynomial function exists everywhere. So back when we did all of this work back in units 3 and 4, we talked about how to factor higher order polynomial expressions, and then factoring to put it in factored form to find the roots of degree 3, degree 4, degree 5 polynomial expressions. We graphed them in different ways. We looked at their characteristics. I hope you remember this stuff, like I said, for the exam. And so polynomial functions have a domain where they exist everywhere. So the product of two of them will also exist everywhere. And algebraically, that'll make a lot of sense when we do that in a few minutes. So let's just get started. So f at x, if I find at -3, that's right here. So it's just 0. And then at -2, it's 1. At -1, it's 2. At 0, it's 3. And it's linear. It's just going up by 1. So 4, 5, 6. And at 4, it should be 7 over to 4, 7. There it is. Right? Pretty easy. G at x, I might start with a couple of the easy ones. So at 0, it's 0. And at 3, it's 0. At -2, it's on the graph. It looks like it's -10. At -1, it's -4. -3 goes off the graph. But we have the equation, so I can figure it out, right? G at -3, it works out to -18, I believe. -9 minus 9. At 1, it is 2. At 2, it is 2. And at 4, it is -4. Easy enough, picking points off a graph. And so how do we find, so remember when we did adding and we literally were adding y values, but it was kind of easy to see how they add. Well, it's a bit harder. It's maybe worthwhile going back after we graph it. It's a bit harder to see the product of two because it just changes so much compared to adding two functions. It's a little bit easier to see. So that's why we're doing it with a table. So I suppose this is a strategy you could use to just find points. But we're really just exploring here. So 0 times negative 18, well, that's 0. 1 times negative 10 is negative 10. 2 times negative 4 is negative 8. 3 times 0 is 0. 8, 10, 0, and negative 28. Do you notice anything? Like what jumps out at you when we sort of go through those values? Anything? Bishoy? There is some symmetry of some type going on there. Yep. What else? Okay, good. I'm not sure how you figured that out yet, unless you sort of thought about what's going to happen, but very, very good. What else? I don't think it's obvious from the table. That's all right, Aaron. Or maybe it is. Anything else? Hunter? Okay, very nice. And where did the zeros occur? Well, they occurred where either of the original functions were 0, right? Because if they're 0, you multiply by anything, you're going to get 0. I don't know if that's very helpful necessarily, but that's just kind of a pattern to think about. If one or the other was 0, then the product of them is 0. I mean, that's something we know well. Okay, let's plot these points. So, negative 3 and 0. Negative 2 and negative 10. Negative 1 and negative 8. 0, 0. 1 and 8. 2 and 10. 3 and 0. And so look where, just graphically, where f at x or g at x, where there's an x-intercept, there's an x-intercept of the product, right? It's the same idea. And then the next one goes off the graph. And as Aaron pointed out, it's cubic. Absolutely. The product, and if you go back and think about this, the product of two polynomials will be a polynomial. So let's look at this algebraically. This is equal to f at x times g at x. Just a matter of notation, but that's not usually how we write it. So this is x plus 3 times negative x squared plus 3x. Go ahead and expand that. Did you get that? And if this were like unit 1, not really unit 1, but back unit 1, unit 3, unit 4 days, and we wanted to know a little bit more about this, this function, the graph of this function, or the nature of this function, its characteristics, what would we do? Zoe? Factor. So I'm going to factor out a negative x, and I'm left with x squared minus 9. That worked out nicely. Negative x, x plus 3, x minus 3, and we start to see a lot of characteristics of that cubic function that we just graphed. It's got a negative leading coefficient. It's got 3 zeros, obviously it's cubic. And there's the zeros right there, 0 and 3 and negative 3, right? We see all of that coming out. Nice little reminder about how all of that works. But really it's just like the product of two functions. At the same domain element, you multiply the y values together or divide them. There's work practice today from two sections of the textbook because they split it up into products and quotients, but quotients is really short. It's like 3 questions. Okay. If you don't have this printed out, I wouldn't bother writing it down. You can look at it after. Here's the example where it starts to get really interesting and you see the power of this stuff. That's why it's too bad we can't kind of do more of it. So a pendulum swings back and forth, and because of friction or because of air resistance or whatever it is, right, it's losing 10% of its amplitude each swing. So the displacement of the pendulum from its center position, okay, so how far it's swinging out to the side, can be modeled by the product of a sine, because without friction, the pendulum would swing back up to the same distance or the same displacement out from the middle every time. But we know that every time it's going to swing a little bit less far, 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 right? And eventually it's going to come into the middle and be doing this. Like a ball bouncing doesn't bounce up quite as high every time. So if we take a sine function and combine it as a product with an exponential decay function, then you can get a very accurate model of this situation. So the functions that I chose are 2 times the sine of pi x. Don't worry too much about that, but you can think about, oh, what's the period, what's the amplitude, think about all that. The amplitude's obviously going up to 2, down to negative 2. And then a graph of 0.9 to the x. And you see that graph is the green one going below. But all we're going to do is think about the product of these two. So let's just watch carefully for a moment here. And this is like 2 times a little bit less than 1. Right? This is 1. So what's 2 times 1? 2. So what's 2 times a little bit less than 1? A little bit less than 2. So I would put a dot just below 2 there. And then this is negative 2. So this is a negative times a positive, so it's going to be negative. And my curve was less than 1 here. Well, now it's still just a little bit less than 1, but it's more less than 1 because it's a little bit lower, right? So this point is going to be like within negative 2, but by a bit more. So where exactly is kind of hard to estimate, and I'm not too worried about you estimating those really, really well. But you kind of think about them and do your best. Okay, keep going, like if you were doing this in your homework or on a test or something. And then the next one is 2 times a little bit less than 2 again, but not half. This is half. So 2 times a half would give me 1, so it's not there. So it's still like up here. In fact, it's higher than that. It's going to be right around there. And then a little bit less, so that's going to be right around here. So you notice I'm getting like, I'm coming in more and more and more every time. Okay, and then even more. And even more. And this one is where I have about 2 times a half. So that's where this is going to now be 1. Okay, and then negative 2 times less than a half, so it's going to be less than 1. Negative 2 times more less than a half. Times even more. And even more, something like that. Not quite a quarter, that's probably too much. So what would this look like? just like what you would expect it to look like. Kind of like a sine curve that's getting smaller and smaller and smaller. Pretty powerful stuff when you think about comparing it, to the real world. So let's see. These are not the exact same numbers, I don't think, because I've changed this. That might be the right one right there. And if I decrease this, you can see how it has an impact on the blue guy getting smaller there. Or if I change that, you can really do some different things there when you start playing with the product of two. Any questions about any of that?